Okay, so I'm going to do a quick demonstration video of logistic regression with this data set. This is the Haberman data. It comes from this study. The data set contains cases from a study that was conducted between 1958 and 1970 at the University of Chicago's Billings Hospital on the survival of patients who had undergone surgery for breast cancer. There are 4 variables in this data set: the age of the patient at the time of their operation, the patient's year of operation, the number of positive axillary nodes detected, and the survival status. So if they were coded 1, it means that they survived 5 years or longer, and if they were coded 0, the patient died within 5 years. So for homework, you're going to conduct a binary logistic regression and an ROC curve analysis where you predict survival status with just these two variables, age and number of nodes. And you're going to report all your findings in APA. So I want it to look like this, plus I want you to add the area under the curve analysis here. So you're just going to report that the area under the ROC curve was whatever it turns out to be, and give me what you think it is. You can throw in the citation or you don't have to, but I do want this. Okay, so let's go to our data and let's take a look. We have age, year of surgery, nodes detected, and survival status with 0 is they died and 1 is they survived. Okay, so the first thing we want to do is run our multiple regression to make sure that we don't have any multicollinearity, which is when we have too much correlation between the independent variables. So we're going to go to regression, come down to linear. I've already done it. Let me start over. So we want to predict survival status with, we're going to use year of surgery and nodes detected. For this demonstration, you're going to use age and nodes detected. So the only thing we really want to know are collinearity diagnostics. So I'm going to say OK. And I come down here and I see that everything's less than 5, and we're good to go. Okay, so now let's run our logistic regression. So we go to Analyze, Regression, Binary Logistic. I have survival status as my dependent variable. I want year of surgery and nodes detected as my independent variables. I don't have any categorical variables. I'm going to go to Save and ask for probabilities and leave that one checked. All right, then I'm going to go to Options. I'm going to say Classification Plots, Hosmer-Lemaichau, confidence intervals for the exponentiated betas, case-wise listing of residuals, and then at last step, and leave the constant in the model. All right, then I say Continue, and then I say OK. All right, so we'll scroll down. We see our groovy table, and we can see that we have one outlier, but we're going to just leave it. So let's look at our null model. So block 0, you can see that without any predictors in the model, we still are classifying 73.5% correctly, which is kind of high for not having any predictors. All right, so we come down to enter the block 1. All right, and we want to look at this model, and we see we have a large chi-square value, 2 degrees of freedom, highly significant. So these predictors do significantly predict the outcome variable. Our Nagel-Kirky R-square accounts for about 10.6% of the variation in the dependent variables predicted by the independent variables. Our Hosmer-Lemaichau test is significant, so we don't have a very good fit. But that's okay, we'll just keep going. We kind of ignore this table. We come down to our classification table, and we'll come back to this in just a second. I want to look really quickly and see which ones are significant. So we can see that year of surgery is not a significant predictor of the outcome variable, but the number of nodes are. Now remember, here we typically in a multiple linear regression, we would look at our betas, but we're going to come over here and look at the exponentiated betas. And remember, our outcome variable is those who survived. So for every unit increase in nodes, you are less likely to survive, because that's less than 1. All right, let's look at our. All right, so sensitivity is true positive. So that is those with the condition who are correctly classified. And so that's 216. So those who survived, who were also correctly classified as having survived, and that's 96%. Specificity of the true negatives, so those who died and those who also died with, in the observed category, and that's 14.8%. So we have good sensitivity, we don't have such great specificity. And remember, this column is our positive predictive value, so that is 216 divided by 69 plus 216, and that's 75.8% is our positive predictive value, and our negative predictive value, that's 12 divided by 9 plus 12. When you do that out, it's 57.1% is our negative predictive value. All right, so now let's do our ROC curve analysis. So we can come down here to classify. We'll go to classify, come down to ROC curve, and we're going to want to, our predictive values is our test variable. Our state variable is the survival status, and we want 1 to be our state variable. We want the diagonal reference line and standard error and confidence interval. And then we just say, we check options. Everything looks good, we say okay. All right, and so we see, we just get a little bit of output. We get the graph, and we can see that we have the area under the curve is 0.71, which according to the classifications from Hosmer, Michel, and Sturdivant, 2013, that is considered acceptable discrimination. All right.